Greetings. Hope you are doing fine in this short holiday for 10 days. Yeah, my name is Patrick Kamala. I am an educator at Netherlands for mathematics and physical sciences. So today I am happy to take you through this chemical change part 3. That is after marking your papers and seeing the marks. I think we need to do this again. So please don't worry about what you covered, but I just want you to understand that all things are easy if you put in your time. Now, as we do this, please, my learners from Netherlands grade 10, get your worksheet, that is chemical change part 3, and then you follow your worksheet as we go through this together, because it was not completely done in a class. So I want us to use this opportunity to go through it once more. Okay, now this is to do with stoichiometry. Stoichiometry is a part of chemistry that looks at the relative quantities of reactants and products in chemical reactions. We use stoichiometry to calculate quantities such as amount of products in mass, moles, and the volume that can be produced with given reactants and percentage yield. Okay. Now, mostly here important is the mole concept. The mole concept. Okay. Now, the mole is a unit of measurement and expresses the amount of chemical substances. We use the mole as a unit of measurement because the size of atoms, ions, and the molecules is so small. Okay. So we define the mole as the amount of pure substance containing the same number of chemical units as there are atoms in 12 grams of carbon-12, which is 6,02 times 10 to the power 23 atoms. Then 1 mole of anything contains 6,02 times 10 to the power 23 of that object. Okay. Let me say this again, that 1 mole of anything contains 6,02 times 10 to the power 23 of that object. Like for example, 1 mole of an element in grams contains 6,02 times 10 to the power 23 atoms. Take an example of 1 mole of carbon, which is it's going to be the same as also 6,02 times 10 to the power 23 carbon atoms. And 1 mole of bananas is also equals to 6,02 times 10 to the power 23 bananas. So now this number here, the number 6,02 times 10 to the power 23 is known as Avogadro's number. So don't be scared, Whenever you find this number, the 6,02 times 10 to the power 23 is known as Avogadro's number because it was discovered by this guy called Avogadro. And in chemistry, we abbreviate it as NA. A for Avogadro, then N for the number. That number is 6,02 times 10 to the power 23, which represents the amount of substances in what? In 1 mole. Okay. Alright, let's proceed. Now this number is a very big number. If you write it in full, it has got it is actually 602 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. So it's a very big number. Okay. Now the unit of the mole is written in MOL and is the basic unit of measurement in chemistry. Okay, so we're going to be measuring using moles in our calculations. Okay, now the mass of 1 mole of an element is equal to the relative atomic mass of the element in grams. This is also important. We're saying that the mass of 1 mole of an element is equal to the relative atomic mass of the element in grams. Okay, Let me say it again. The mass of 1 mole of an element is equal to the relative atomic mass of the element in grams. For example, 1 mole, for example, 1 mole, one mole of carbon, I forgot to put C here. 1 mole of carbon, 1 mole of carbon, 1 mole of carbon, 1 mole of carbon has a mass of 12 grams, and 1 mole of oxygen has a mass of what? 16 grams, and 1 mole of helium has a mass of what? 4 grams. Okay, let me say it again. I'm saying 1 mole of carbon, carbon is an element, it has a mass of 12 grams, and then 1 mole of oxygen atom also has what? 16 grams, and then 1 mole of helium, has a mass of what? Of 4 grams. This is 4 grams. So 1 mole is the same as the mass, which is for each element in the periodic table. Okay, let us proceed. Now, the relative molecular mass, that is MR, of a molecule is the combined relative atomic masses of all the atoms in the molecule. For example, the relative molecular mass of water, that is H2O, is what? 1 times 2, then plus 6, which gives us what? 18. Okay. Now, this one is for hydrogen, but because there are 2 of them, that's why we say 1 times 2. What about the 16 here? It is for the oxygen, which is 16. So that you get 18 here. So the 18 grams is the relative molecular mass of what? Of H2O, which is water. And then the relative formula mass of an ionic substance is the combined relative atomic masses of all atoms in the ionic substance. I'm saying that the relative formula mass of an ionic substance is the combined relative atomic masses of all atoms in the ionic substance. For example, the relative formula mass of sodium chloride is 23, that is for sodium, then 35,5 for chlorine, which gives us what? 58,5 grams. Okay, let us proceed. Then the molar mass of a substance is the mass of any substance relative to the amount of substance. Actually, the molar mass of a substance is the mass contained in 1 mole of that substance. So, let me say it again. The molar mass M of a substance is the mass contained in 1 mole of that substance. So, the molar mass is the mass of 1 mole of the substance. Okay. Let me highlight this because you can ask it in your tests. What is molar mass? The molar mass is what? Is the mass of 1 mole of a substance. The mass of 1 mole of a substance. Let us proceed. Quick example. Find the molar mass of 2 ammonium chloride. Okay, 2 ammonium chloride. Now, what we do here? We use our periodic table to get the masses. Okay. So nitrogen, hydrogen, and chlorine. After getting those masses, we're gonna add them together and then multiply by 2 because of these 2 here. So now from periodic table, the atomic masses for nitrogen is 14. What about hydrogen? Hydrogen it is 1. What about chlorine? It is 35,5. So you see there are 4 hydrogen atoms here. It's gonna be 4 times 1. What about nitrogen? It's only 1 nitrogen, also 1 chlorine atom. So it means I'm gonna have it as what? It's gonna be 14 plus 4 times 1 plus 35,5. So and then multiply by 2 because of the 2 which you saw here. So it gives me finally what? It gives me 107 grams per mole. Because now this 107 grams, it is the mass in 1 mole. Okay, actually these are now 2 of them. That is pure ammonium chloride. These are 2 moles here. Okay, let us proceed, guys. Let us look at the mole formulae and the calculations. Now the number of moles, mass, and molar mass. Please pay attention here, guys. Now chemistry is a chemistry of moles. So because of that, not from the start, that moles n, small n, mass m, and molar mass, they have got a relation, they have got a formula which is n equals to m over molar mass, whereby n is the number of moles, the mass must be in grams, and then the capital N is the molar mass in grams per mole. Now this n can also be gotten in other ways, as we're going to see as we put in this particular topic. Okay, because chemistry is a chemistry of moles, so we have so many ways of getting moles, as we're going to see shortly. Let us proceed. Let's take example 2. How many moles of substance are represented by the given mass of each substance here? So they say 19 grams of sodium atoms. Sodium is 23. They gave us the 19 grams. So the formula says N equals to mass over molar mass. What's our mass given here? It is 19 grams. What about molar mass? It's 23. So if you divide this, you're going to get what? 0.83 moles. So the 19 grams of sodium atoms contain what? 0.83 moles. Let us proceed. So don't forget formula. N equals to mass over molar mass. Then we substitute and get our answer. Part B says 35 grams of anhydrated copper 2 sulfate. Now they gave us the small mass, that is again the 35 grams here. Then molar mass for copper 2 sulfate, we get it from periodic table. Now copper is 65. What about sulfur? 32. What about oxygen? It is 16. Maybe you can say you want to see this. Let me show you this one here. But I think you know that, guys. Copper is 60 what? 63.5. Let's check it out anyway. Copper, where are you? Copper is here, 63.5. What about sulfur? Sulfur is here, it is 32. Okay. Yeah. What about oxygen? It is 16. So copper 2 sulfate, we're going to do what? We're going to compute it by using these values here. So with the copper, we thought it is 63.5. What about sulfur? It is 32. What about oxygen? It is 16 times 4. So if we simplify this one here, it gives us what? 159.5. So after getting our answer here, it gives us 0.22 moles. In other words, the 35 grams of this copper 2 sulfate contain what? 0.22 moles. Let us proceed. What about the number of moles in 39 grams of carbon tetrachloride? Now this carbon tetrachloride it's like this one here. Let me show you something here. It's given by C, okay, and then chlorine, that is Cl. Because of that tetra, there are 4 of them. In other words, we have carbon, like we've got one carbon atom here, okay, surrounded by 4 chlorine atoms. So because of being 4, that's why we call it tetra. So this is Cl here, another one is here, another Cl here, another one is here, and another one here. Okay, so now because they are 4 surrounding the carbon atom, that's why I call it carbon tetrachloride. carbon tetrachloride. Okay, now carbon has got a mass of 12. What about chlorine? 35,5. Okay, so if I want to compute this, I'm going to say it's going to be 12. That's for the carbon, which you see here. What about Cl4? 35,5 times 4. So if I simplify this, I'm going to get what? 0.25 moles. 0.25 moles. So please don't forget that. If they say calculate the number of moles and they give you the mass and then the formula, so just use N equals to M over molar mass, then you substitute and get your number of moles in moles. That is interesting, ne? Let us proceed. Another example, they say calculate the mass of each substance for the given number of moles. So sometimes they can give us the moles and then they want the mass. For example, 2,1 moles of lead oxide. So now lead oxide is PbO2. Now note here that they gave us the moles and the formula, so it means we can find what? The mass. Now because we know the formula for lead oxide, that's PbO2, and we know the number of moles, that's 2.1. It means that after writing your formula, after we said that moles n equals to what? Equals to small m divided by what? By the molar mass. Ne? So now that we know the formula, then we can find the molar mass from periodic table again. So as you can see from here, if I make my small m the subject of the formula, I'm going to have my mass equals to what? Equals to the number of moles given to me multiplied by what? Multiplied by the molar mass from periodic table. From where? From the periodic table. So when I compute that, when I substitute that, actually I get something like this one here. So this is moles times molar mass. Okay, so they gave me 2,1. You see that it's here. The molar mass for lead oxide. Now lead is 207. Now oxide, that is O2, is going to be 16 times 2. So if I simplify it on here, it gives me what? It gives me finally 501,9 grams. That's the mass for what? For lead oxide contained in 2.1 moles. Let us proceed. They say 1,5 times 10 power negative 3 moles of lithium phosphate. So you do the same thing here. They gave you the moles. Lithium phosphate is PO4, that is Li3PO4. So compute the molar mass. Then using the formula again, substitute and get your mass. Get your mass. By cross multiplying, ne? You're going to multiply the moles times the molar mass, which gives us a mass of what? Of 0.17 grams. Okay, so hope that was pretty simple. Let us proceed to the percentage composition. Percentage composition of a compound is a relative measure of the mass of each different element present in the compound. As in, we measure the mass of each element divided by the total molar mass times 100. Let me say it again. The percentage composition of a compound is a relative measure of the mass of each different element present in the compound. Work example here. Calculate the percentage composition of sulfuric acid. Now sulfuric acid is H2SO4, and from periodic table we can compute it on here to get 98, which gives us 98 here. Now as you can see, hydrogen, there are 2 atoms, that means 1 times 2, which is a 2 here. What about sulfur? Sulfur is only 1 atom. What about oxygen? There are 4 atoms, that's about 16 times 4. So after getting my total molar mass, which is 98, I'm going to get each one separately divided by the total times 100. So look at hydrogen, it's going to be 2 divided by what? 2 divided by 98 times 100, which gives us what? 2.04%. What about for sulfur? It's going to be 32 divided by 98 times 100, giving us what? 32.56%. What about oxygen? It's going to be 64 divided by 98 times 100, gives us what? 65.31%. So after knowing the percentage composition, that brings us to empirical formula. What is the empirical formula? What is the empirical formula? Empirical formula. Now, the empirical formula of a chemical compound is the simplest whole number ratio of atoms of each element in a compound. Let me highlight it again. I'm saying that the empirical formula of a chemical compound is the simplest whole number ratio. So this must be whole numbers. We don't need decimals, we don't need fractions, no negatives. Okay, so they must be only whole numbers. Okay, no decimals, no fractions. Okay, so the simplest whole number ratio of atoms of each element in a compound is known as what? Empirical formula. Okay, let us see how to do it here. We can take example. They said that find the empirical formula for a compound consisting of 63% manganese and 37% oxygen. Okay, so what do I have here? I have 63% manganese and 37% oxygen. So now if I consider 100 grams, I am going to have something like this. I'm going to have for manganese, don't forget 63%. What about oxygen? It is 37% in 100%. Okay, so now for me to get my empirical formula, please note the steps. I get my moles first, given by mass over molar mass. That is for manganese and oxygen. So look at my mass given to 63%. I'm going to say 63 divided by 55. That's for the manganese. What about oxygen? I'm going to say 37 divided by what? By 16, because oxygen is 16. So when I simplify here, I'm going to get 1,145 moles. What about here? 2,3125 moles. Now listen to something here, please. It's very important. Now when we get here, after getting these moles, listen carefully. After getting these moles for each of the elements, then you check which of the elements, which of the moles is the smallest. Is it this one here for manganese, or is it the one for oxygen? Which one is the smallest number? Check here. This is 1,145. What about here? 2,3125. So the 1,145 is smaller. So that's what we divide. When we reach this step, we divide by the simplest number, by the lowest number of moles throughout. Okay, so here, when I do so here, this one is going to cancel here with this one here. If I divide this one, I'm going to get what? I'm going to get 2,02. So here I got actually 1/1. So 1 divided by 1 is this one which you see here. Now the 2,02 is approximately what? It's approximately 2. So in other words, it's going to be 1 to 2. So this is my simplest whole number ratio, meaning I need 1 manganese to combine with the 2 oxygen atoms, or you can write it as what? As MnO2. MnO2. Now this is a class activity here. Class activity, please try it again. Try it out and see if you understand what we discussed. If you don't understand the activity, please pause the video and replay it again. Okay. Here they want percentage composition, but let us proceed. Let us do one here by the way. Which one should we do here? This is barium nitrate. Now to make this one simple for you, I'm just going to give you the formulas. Then barium nitrate is Ba. It is Ba. Okay. Barium nitrate. Okay. So barium is which group? Is it group 1 or group 2? Let's check it out first. Now barium, check here. Barium is Ba. It is here. It is group 2, ne? So it means it's got valence 2. So if I come back here to my formula for barium nitrate, it's going to be Ba. Now nitrate has got only a -1, ne? So barium nitrate will be like this, and here it's going to be Ba, then nitrate, that's NO, then 3 here, then O3, barium nitrate. Okay, so here, it's here, then. So because barium is in group 2, that's why there's a 2 here. So that's barium nitrate. Okay, so you can go ahead and find what? The percentage composition. What about calcium phosphate? Now calcium phosphate, it is Ca for calcium. Okay, like this. Okay, what about phosphate? Can open brackets again. This is PO4, then close bracket again. Now calcium, like barium, it's also in group 2, so I'm going to put a 2 here. And then phosphate has got 3 minus, so maybe 3 here. So guys, if you want the percentage composition of calcium phosphate, you're gonna get what? You're gonna get 3 times molar mass for calcium, then plus 2 open brackets into phosphorus molar mass times oxygen, which is 4 times 16, then get your total molar mass, and then you continue as we discussed before. Maybe you can say, why don't we do this and we see what happens? Okay, just try it out anyway. I'm doing one for calcium phosphate, ne? Okay, so we have calcium. Separate it here. What's the molar mass for calcium, by the way? Let's check it out. Now calcium, it is 40. You see there's a 40 here. Okay, but how many are they? They are 3. It's gonna be 40 times 3. 40 times what? Times 3. Okay, I'm looking for the percentage composition, ne? Then plus. Okay, what about phosphorus? Let's check phosphorus. What's it? C molar mass. Now phosphorus, it is P. Where is it here now? What is its molar mass? For phosphorus, molar mass for phosphorus, where are you? Okay. Now phosphorus molar mass, where are you? It is here. It is 31. It is what? It is 31 for phosphorus. Hope you've seen it. Let's take it back now. 31 here. But because of these 2 here, which you see, I'm going to say plus 2. Open brackets. I'm going to say now 31 for phosphorus. Okay. What about oxygen? Oxygen is 16. And 16 times 4. What is 16 times 4? Talk to me. What is 16 times 4? What is what? What is 16 times 4? Now when I close my bracket here, I'm going to close it twice, because the third one, the 2 is for both that one and this 16 times 4. So let me get my answer now. I've got 40 times 3, that's 120. So plus 2 into what? Okay, I'm looking for the total molar mass. That's my M. It's gonna be 40 and 120 plus what? Let's take it maybe 120. That is for calcium alone. Then plus, what about phosphorus? 2 times 31, which is 60 what? Which is 62. 62 here. Now the 62 is for the phosphorus, okay. Then plus, what about oxygen? It's gonna be 2 times 4 times 16. Let's look on our calculator. 2 times 4 times 16. 2 times 4 times 16. 2 times 4 times 16, 2 times 4 times 16, you get 2 times 4 times 16. What do we get, guys? We get 128. 128 is what we get here. 128. Okay, so 128 is what I have here. It's 128. 128. Okay. Now, what's my total? 128 plus 120 plus 62. 128 plus 120 plus 62. 128 plus 120 plus 62. 128. Okay. Let's start again. 128 plus 120 plus 62, right? Yes, let's get our answer here. It is 310. It is what? It is 310. 310. 128, 120, then 62. Is it? Yes. So you get 310 here. You get 310. Now, to get my personal decomposition, I'm going to get each one separately. I'm going to say 120 divided by 310 times what? Times 100. That's for, okay. That's for what? That's for the calcium. It's going to be 120. 120 divided by 310 times 100 times 100. So which answer do we get here? Which answer do we get? Let me check it out faster here. So 120 divided by 310 times 100, 38,7. 38,7. So I get what? 38,7%. So this is the percentage of what? Of the calcium in calcium phosphate. Okay. I go ahead to get down for phosphorus. Now I'm going to use 62. I'm going to say 62 divided by the total times 100. Okay. 62 divided by what? By 310 times 100. 62 divided by 310 times 100. What do we get here? 62. Yeah, gives us 20%. Gives us what? 20%. Gives us 20%. So we do the same thing, guys. Even for oxygen, you're gonna use what? 128, né? So if I use 128, I'm gonna get now I'm getting 41.3%. So it's gonna be 41.3%. Check it out, please. If you don't know how to do it, pause the video and do it again. 41.3%. So this is the percentage composition of what? Of the calcium phosphate. Okay, hope you're together, guys. Let us proceed. Next, question 6 says determine the empirical formula for each compound with the given percentage composition by mass. Okay, so what do we do here? I did that already. Let us proceed to something else. Okay, let's check here. Something is interesting down here. Here, number 5 is about water of crystallization. Water of crystallization is the total mass of water retained by certain salts at given temperature and is mostly present in what definite ratio. Now, the water of crystallization is necessary for the maintenance of a salt's crystalline properties, but can be removed by sufficient heat. By sufficient heat. And the water is in the crystalline framework, but is not bonded to the ions of the crystal. Okay. Let's take example. Calculate the percentage of water crystallization in copper 2 sulfate 5 water. So what do we do here? Again, get your molar mass for copper 2 sulfate 5 water in total. Now copper 2 sulfate, like we said, the copper is 63.5. What about sulfur? It is 32. What about oxygen? It is 4 times 16 because of the 4 here. And then plus 5 water. So this 5 is the 5 which you see here. Then water is 2 times 1 plus 6, which is 18. So if you take this out, we see that we're going to get something like this. We're going to get 159.5. That is for the copper 2 sulfate, and then 90 for the 5 water. So because we want the percentage water of crystallization, we're going to divide this 90 by the total. This is a total here. Then times 100. Times what? Times 100, which gives us 36.07%. Okay, so I hope this one is also quite simple. Let us proceed. This worksheet is a little bit bigger. So this is a class activity here. Try it out. Yeah. Let's continue with the concentration of solutions here. Concentration of solutions. What is concentration? Now here I saw many learners having different definitions. Somebody said concentration when look at something and look at something and not look at something else. Hey, my friends, this is here in chemistry. The concentration of a solution is a measure of the amount of solute that is dissolved in a solvent, and the solution can be made less concentrated. That's by adding more solvent. Now, if we ask you again to define concentration, this is what you must say, guys. This is what you must say. What is concentration? It is the number of moles. The number of moles of a solute dissolved in 1 liter of a solvent. I'm saying that concentration is the number of moles of a solute dissolved in 1 liter of a solvent. All you can say, in 1 decimeter cubed of a solvent. Now, the concentration changes when more solute is added. Like if you got sugar and you put in water or in tea, the more sugar you add, the more concentrated your tea is going to become. Now, there's a formula which we use here to get our concentration. That is C equals to N over V. If they say calculate the concentration and they give you the moles and the volume, then you can use C equals to N over V, whereby N is what? Number of moles. What about V? Volume in decimeters cubed. Volume in what? In decimeters cubed. Don't forget the formula. C equals to N over V. N is number of moles. V is what? Volume in decimeters cubed. Now, we have got something to note in our calculations here. If they give us a question in and the volume is centimeters cubed, please, we must now convert it to decimeters cubed. What do? You divide by 1,000. For example, 125 cubic centimeters same as what? 125 divided by 1,000, giving us 0.125 decimeters cubed. Let us proceed to something else here. Also, 1 milliliter is the same as 1 cubic centimeter, and then 1 liter is the same as 1 decimeter cubed. Please don't forget those in your calculations. We'll take example here. Calculate the concentration of sodium chloride solution containing 0.125 moles sodium chloride in 500 cubic centimeters of water. So here, note what they gave us. What have they given us here? They say calculate what? The concentration of what? Of sodium chloride containing what? These moles here. These moles here. Okay. They gave us a volume which is what? 500. Now, this volume is in centimeters cubed. So what do? We convert it to decimeters cubed by doing what? By dividing by 1,000. Now, the formula says C equals to N over V. Our N is defined at 0.125 moles. What about V? We must put it in decimeters cubed. So divide by 1,000, which gives you what? 0.5. So when you compute it on here, it gives you final as what? 0.25 moles per decimeter cubed. 0.25 moles per decimeter cubed. So if they say calculate the concentration and they give you moles and the volume, that's how you get it. Okay. Let us proceed, guys. They say calculate the number of moles of copper 2 sulfate solution of 0.02 moles per decimeter cubed in 250 ml in water. Now this time, what have they given us? Check what we have. Now this time, they gave us concentration. They want number of moles. Also gave us the volume. But the formula says C equals to N over V. So now what do they want actually? They want the moles N. They want moles N. Okay. And then they gave us what? They gave us the concentration C. Also gave us the volume V. Okay. So you know that C equals to N over V. Like you see it here, guys. C equals to what? C equals to N over V. So my C is 0.02 moles per decimeter cubed. What about my number of moles? That's what I'm looking for. What about my volume? Now, mils are the same as centimeters cubed. So, but I must use what? Decimeters cubed. What did we say? Divide 250 by what? By 1,000. Okay, so what happens then? We get 0.25. So now here I cross multiply to get my number of moles. N equals to 0.02 times what? Times 0.25, which gives us what? 5 times 10 power negative 3 moles. Gives us what? 5 times 10 power negative 3 moles. Okay. Next question here. Calculate the volume of a 0.8 moles per decimeter cubed potassium bromide solution containing 1.6 moles of potassium bromide. What have they given us this time? They want the volume, ne? They want the volume. They gave us a concentration again. And they said it's for what? For potassium bromide. So we can get the molar mass if we want to use it there. But they gave us moles anyway, containing these moles here. So they want the volume, they gave us moles, and the concentration. What does the formula say? C equals to N over V. So if you substitute here, you're going to have what? You're going to have 0,8 equals to 1,6 divided by V. So here cross multiplying, it's going to be V times 0,8 equals to 1,6 and divided by 0,8 both sides, which gives you what? 2 decimeters cubed. Now that's our volume which we have here, 2 decimeters cubed. Okay. Another example here, they say calculate the concentration of if 17 grams of silver nitrate dissolved in what? In a 250 cubic centimeters of water solution. Now here they gave us the mass. Now look at this, guys. They gave us the mass. Also gave us silver nitrate. If we can get the formula. Then we have the volume in centimeters cubed. What are we looking for? Calculate the concentration. Calculate what? The concentration. So C equals to N over V. Don't forget our formula. C equals to N over V. What about our N? Anybody who remembers how to get N? N equals to mass over molar mass. So the mass given to us is what? 17 grams. We can get the molar mass here for silver nitrate from the periodic table. And then what happens next? Let's check it out here. Now if you look at C equals to N over V, we can first get the number of moles, that's mass of molar mass, which gives us what? 0,1 moles. But what does our C equals to? C is N divided by volume, ne? Now our volume, it is also in decimeters cubed now if you divide it. So this is 0,1 over 0,25, giving us what? 0,4 moles. Hope we are still together, guys. Let us proceed. Calculate the mass of lithium carbonate used to prepare a 0,36 moles per decimeter cubed solution of what? 250 mils of water of the solution. So I want the mass again, ne? I want the what? The mass. They gave me the concentration and the volume. So C equals to N over V. What about N? N equals to mass over molar mass. So if I combine these two equations, I get C equals to M over molar mass. C equals to what? To mass. That's the mass divided by molar mass times volume. Ne? Let us proceed here. Now this mass is what they gave me. This is what I'm looking for, kids. I can get molar mass because I know it's from what? Lithium carbonate. Ne? They gave me the volume and the concentration. So if I substitute, this what I get here is something like this one here. So if I compute this one here, I get what? Now this is my concentration. They want this mass. I got the molar mass already times the volume, which is 0,25. So if I cross multiply again, I'm gonna get what? The mass of lithium carbonate equals to 0,36 times 74 times 0,25, which gives me what? 6,66 grams. 6,66 grams. Okay. Class activity is here. Let's see, class activity is here. Please try it out. After getting the solutions, you can inbox me and we check if you're correct or not. Let us proceed. It continues here. Okay. Actually today, what I wanted mostly to do is talk about molar volume. Okay. And here we are finally, the molar volume. molar volume. Okay, now molar volume is the volume contained in 1 mole of a gas at STP. Let me highlight this. If we say define molar volume, what did it say? That molar volume is what? Is the volume contained in 1 mole of a gas at STP. So what's molar volume? It is the volume contained in 1 mole of a gas at STP. Now teacher, what does STP mean? Now at STP, that is standard temperature and pressure, 1 mole of any gas has a volume of what? Of 22.4 decimeters cubed. Note something here, we're saying 1 mole of any gas, whether it is oxygen, whether it is hydrogen, whether it is nitrogen, name it, any gas at STP, that is at standard temperature and pressure, it has got a molar volume of what? Of 22.4 decimeters cubed. Please note, listen down guys. We're saying that at STP, the molar volume of any gas is what? Is 22.4 decimeters cubed. What is molar volume? The volume contained in 1 mole of a gas at STP. Now STP means standard temperature of what? Of 0 degrees Celsius, which is also the same as 273 Kelvin. Okay. What about the pressure to be standard? That is 101.3 kilopascals. That's what we mean by standard pressure. What about the atmosphere? Rather the pressure. Now the pressure is the 101.3 kilopascals, which is the same as 1 atmospheric pressure. So if we ask for the standard conditions, don't forget 1, that is 0 degrees Celsius, then 2, it is 101.3 kilopascals, and then 3, you can also say it's 1 atmosphere. So standard temperature and pressure. The temperature is 0 degrees Celsius or 73 Kelvin. What about pressure? You can say it's 1 atmosphere or 101.3 kilopascal. Let us proceed, guys. Look at the calculations here now. Okay, now we talk about 1 mole. So for example, 1 mole of oxygen has a molar mass of what? Of 32 grams per mole, which you get by multiplying 16 times 2. The mass, not 1 mole of oxygen, has a mass of what? Of 32 grams per mole. What about the volume? It is 22.4 decimeters cubed, where at STP. So 1 mole of oxygen gas has a molar mass of what? Of 32 grams per mole. What about its volume? It is what? 22.4 decimeters cubed at STP. Take another example of another gas, hydrogen. Now 1 mole of hydrogen gas has a molar mass of 2 times 1, which is 2. What about the volume? Amazing, it is also 22.4 decimeters cubed. Another gas now. What about nitrogen gas? Molar mass is what? The molar mass, it is the molar mass is 28 gotten by what? 14 times 2. What about the volume? It is still what? 22.4. Now as you can see, I have the same 22.4 for oxygen, 22.4 for hydrogen, and 22.4 for nitrogen. So it means that, guys, this is a constant. As long as the question says STP, then please know that the mole of a gas at STP is what? It is 22.4 decimeters cubed at STP. Now something to note here. equal volumes of all gases under the same conditions, that is to say, same temperature and pressure. They contain the same number of what? Of particles. Let me say it again. Equal volumes of all gases under the same conditions contain the same number of what? Of particles. Okay. Now, the volume of the gases that react or are produced in a chemical reaction are proportional to the number of moles. Let me explain what I mean here, guys. This is what I mean here. As in, if I have nitrogen gas reacting with hydrogen gas to give me ammonia here. Now there is one here. Okay, you see that one there. That means one nitrogen plus 3 hydrogen gas to give me 2 ammonia gas. So, in other words, 1 mole of nitrogen plus 3 moles of hydrogen gives me how many? 2 moles of ammonia. Now, likewise, even if I consider now volumes, and I say that 1 volume, because of this one here, reacts with how many? 3 volumes, because of the 3 here. Produce how many? 2 volumes, because of the 2 which is here. Now, because 1 volume at STP is 22,4 decimeters cubed, that's why it is like this one here. Now, because of the 3 here multiplied is 22,4 times 3 gives me what? 67,2 decimeters cubed. And because of the 2 here, multiply 2 times 22,4 gives us what? 44,8 decimeters cubed. Okay. Let us proceed, guys. Let's proceed here. Now we can find the proportions using algebra. Okay, now I don't want to waste your time here. Let me go to examples straight direct to see how it works here. The question says find the volume of oxygen that will react completely with 500 cubic centimeters of what? Of sulfur dioxide gas at STP in the reaction below. What do I have? Find the volume of oxygen. You need volume of oxygen. That will react completely with what? 500 cubic centimeters of sulfur dioxide. In this equation here. Okay, now check this out, guys. Now I have the volume, which is 500 cubic centimeters. Look at my mole ratios. That is 2. This 2 which you see here, plus 1. This is the one here. This is the one here. To give us 2, there's another 2 here. So the mole ratio is what? It is 2 to 1, then to 2. So in other words, if I want to calculate volume of oxygen react with this sulfur dioxide, now my volume is given in centimeters cubed. So what must I supposed to do? I'm going to divide by 1,000, which gives me what? 0,5 decimeters cubed. Okay. Okay, what does the formula say? Let's get your mole ratios first, and then the one you're looking for, you can put X or Y, like number of moles of oxygen. Though we want volume. So because you know that after getting moles, you can get a volume. Did you hear that? Let me say it again. After getting number of moles, we can get what? The volume. The question is, how do you get number of moles? Talk to me. How do you get the number of moles here? Okay, we're going to use our Molar ratio, then we're going to cross multiply. It's simple algebra, don't worry about this, guys. Look at my equation again. That is 2 sulfur dioxide plus oxygen, 1 oxygen to give me 2 sulfur trioxide. What's my Molar ratio? 2 reacted with 1 to produce 2. In other words, they're given 0,5 react with x. Okay. So I'm going to cross multiply now. Not this, I'm going to say 0,5 multiplied by 1 equals to 2 multiplied by x. What should I know is x? That is 2x. That's 2 at 2x. What about 0,5 times 1? That's 0,5. So I divide by 2 both sides, which gives me what? Which gives me 0,25 decimeters cubed. Okay, more weight examples on molar volume. Okay, let us proceed here. Study the balanced equation below, that is nitrogen plus hydrogen to give us 2 ammonia. Let's say convert 250 centimeters to the correct SI unit for volume. Now, volume must be in decimeters cubed. So what do we do? Divide by 1,000. Divide by what? By 1,000. Divide by 1,000. Which answer do we get here? Gonna be 0,25, 0,25. Now that's my decimeters cubed, or you can say these are liters. Okay. Now another question says, if 22,4 decimeters cubed of nitrogen reacts completely with hydrogen, calculate the volume of ammonia that forms. Okay, so what do we do here? What do we have here? Let us check the solution here. Now nitrogen plus 3 hydrogen give us 2 ammonia. What's our Molar ratio? 1 to 3 to 2. Don't forget, we must balance this one first. So I want to know how much ammonia will be produced if I react what? The 22,4 decimeters cubed of nitrogen. Okay. So not something here, guys. You see, this is 1, this is x. So we cross multiply actually here. We do what? Cross multiply. So gonna be 1 multiplied by x, and then 22,4 multiplied by 2. What do you get? What's 1 times x, guys? Talk to me. That's 1x, That's 1x. And then which gives me what? Which gives me 44,8 decimeters cubed of ammonia that will form. Okay. Let us proceed. Now question 3 was to do with they gave us nitrogen, and they gave us hydrogen, and they want to know how much nitrogen is going to left with this volume here. Okay. So again, what we do here, we simply cross multiply. Guys, look here. Write the molar ratios. Look at for the 2 elements which are required. Write their ratios respectively, and then cross multiply. and then do what? And then cross multiply. Then do what? Then cross multiply. What is 3 times x? That is 3x. And then 1 times 36, 33,6, that is 33,6. So divided by 3, both sides gives you what? 11,2 decimeters cubed of nitrogen. There you go. Okay. Next. This is a class activity here. It's almost the same as the project example we just discussed now. Try it out, please. Try it out. Try it out. Try it out. Try out this class activity. Okay. When you are done, please inbox me your answers and we can take it from there. Thank you so much for watching. This is Patrick Kamala once again. I'm an educator for Physical Sciences Grade 10 and Mathematics at Nurdarand. Catch you in my next video. If you want more videos like this, please you can inbox me or call me on WhatsApp 0785 222 041. Let me say it again, 0785 222 041. Bye bye.